I have graduate and undergraduate degrees in astronomy, physics, chemistry, mathematics, as well as some subspecialties and a few others like geology and whatnot. Rich Groller asked me to give a talk about a star that's been in the news a lot lately, and no, it is not pronounced like the movie. Betelgeuse, not Beetlejuice, okay? Betelgeuse. So the title is called Your Results May Vary. I couldn't come up with a good title. My husband, who happens to be the special guest of honor for LibertyCon, Daryl Osborn, or Doc Osborn, came up with the title for me. So whenever I get stuck, he's really, really good for coming up with stuff like that. Next slide, please. All right. So one of the things that we need to discuss, well, there are several things that we need to discuss to get the whole concept of what's been going on with Betelgeuse, get an understanding of it. We need to know what is a variable star. We need to know how many types there are. And we need to understand why Betelgeuse has caused so much excitement in the astronomical community and in science news of late. Next slide. All right. What not to believe. All right. No, I'm sorry. That is not an actual star image. There's nothing about this photo, including the title, the captions, or anything else, that are real. All right? If you see something like that, go, probably not, and keep going. All right? Next slide. Now, what are variable stars? Very simply put, variable stars are any stars whose light output as viewed from Earth is not constant. Now, there are a number of types of variable stars, and you can break those down into two basic types, intrinsic and extrinsic variables. An intrinsic variable is a star that varies as a result of something the star is itself doing, something internal to the star. An extrinsic variable is something that is causing the light from the star to be blocked. These include eclipsing variables, rotating variables, close or contact binaries, spotted stars, etc. There is something that is blocking the light from the star, whether it be another star, a planet, a star spot, otherwise known to us as sunspots, etc. All right? Intrinsic variables include pulsating variables of various types and eruptive variables, principally. Next slide. Now, it's kind of a pretty little breakout diagram. It's very hard to read, so I won't go into a whole bunch, except that that is just a breakout of what I just said. Okay? Next slide. Now, Betelgeuse is one of the brightest stars in the constellation of Orion. It is the top left shoulder of Orion. And I'm not going to go into all the different names it has. Those pertain to star catalogs. It is the 10th brightest star in the night sky. And depending on where it is in its cycle of variability, it is either the brightest or the second brightest star in Orion. And so we have the statistics there. The spectral type is either an M1 or an M2, 1A or AB. It's somewhere between 500 and 6,500 light years away. It is somewhere between 8 and 9.5 million years old. The temperature of the photosphere is about 3,600 degrees Kelvin. Do I need to explain what a Kelvin is as a unit of measure? Anybody that does not know what a Kelvin is? Okay. The radius is anywhere from 760 to over 1,000 solar radii. And note that that is larger, even the smaller number is larger than the asteroid belt and possibly larger than Jupiter's orbit. And the mass is somewhere between 16 and 19 solar masses, 16 to 19 times the sun's mass. Why do so many of these values have a range given? Because the fact that it is very, very bright and it is also variable make it very difficult for astronomers to determine what those actual values are. Next. We have a question?
Sure. Why is the distance so much more variable than all the other values?
Because one of the ways we determine distance is the brightness of the star. And if we don't have a constant brightness, it becomes very difficult to determine distance. Then you start having to look for other factors to get your distance. So we know that it is, you know, at least that far away and maybe further. All right, so this is the constellation of Orion, and I've given you a big fat red star to mark where Betelgeuse is. And yes, Betelgeuse is a red star. Next slide. This is an actual photo of the constellation of Orion. And so you can see Orion's belt quite well. You can see the Great Nebula of Orion as part of Orion's sword. You can also very clearly discern the reddest star in the field, which is Betelgeuse. Next slide. Now, it's not, strictly speaking, part of the Orion molecular cloud complex anymore. It's been ejected from the OB1 stellar association fast enough that it's actually formed a bow shock in the interstellar medium. It most likely was ejected by a supernova event elsewhere in the cloud, but fairly close to where it originated. It may once have been a binary star. Stellar evolution, some people don't understand the concept of stellar evolution. I've had people who are like, but what does Darwin have to do with it? Well, that's just, seriously, I have. Stellar evolution is simply a term that astronomers use to indicate the life cycle of a star. How far is a star along in its development? So stellar evolution may have caused the other star in the binary system to expand first if it was more massive, and if it exceeded its Roche lobe, the excess would have passed through the Lagrange point and fallen onto the other star. In this case, it would have been Betelgeuse. So eventually this could basically cause virtually the complete dissolution of the star. The only thing that would have been left was the core. And if it's possible, since the core would have been considerably smaller, that it wouldn't have been less affected by whatever the ejection event was that sent Betelgeuse hurtling outward. So the two would have separated and we wouldn't necessarily be able to determine where it was. However, it's also possible that the two stars spiraled into each other when Betelgeuse expanded. If so, the estimated time of cannibalism of the companion star would have been about 100,000 years ago, which on astronomical terms is yesterday. What evidence do we have of this? Well, it's a red supergiant. It has a mass so high that it must once have been an O or B class blue supergiant. And those are almost always found in binary systems. Betelgeuse also rotates so rapidly currently that it's actually throwing off parts of its outer layers. Some of the bow shock, at least some, if not all of the bow shock, may be actually be a burp as the secondary was absorbed, a poofing off of some of the outer layers. It has a stellar diameter of over 1 billion kilometers, It's truly, truly a monster star. There are stars out there that are bigger, however. Between the size of the star and its distance, you can actually, our telescopes, our ground-based telescopes can actually resolve a visible disk. You can actually see a tiny, tiny little disk, not just a point object. And so it's about 19 times, on average, about 19 times the sun's mass. That's about in the middle of the range. Notice how big it is compared to Earth. Okay, next slide. This is what I mean when I say it has a resolvable disk. The white center and red surrounding it, that is Betelgeuse. That is the disk of that star. This is in near infrared, and you can read all the stuff there in the caption. Next slide. Now, I said it spun really, really fast. How fast? Well, the photosphere at its equator spins at about 15 kilometers a second. Compare that to the sun's rotation of about 2 kilometers per second at a diameter that is only 1/1000th that of Betelgeuse. This means that the rotational velocity is extremely high, and this is most likely due to the fact that it cannibalized its companion, and that added to its angular momentum. Next slide. Artist's concept, but it gives you an idea of the relative scales. Because the photosphere is rather violently boiling. And I don't know, I think I could have found a better way to depict that than that artist did, but hey, whatever. And then on the right, you can see a schematic to scale of our solar system. Yeah, I saw somebody mouth, wow. Yeah, wow is a good way to put it. Next slide. Now this is a graphic. It's an actual image. It's a combined image. You overlay multiple images of the object and build up the contrast that way. But you can actually see the shock front up there on the top. Obviously, this is false color imagery, but you see Betelgeuse, and then you can see at the bottom you can see the shock front. At the top, you can see the shock front. Now, given that it looks like it continues around, it is possible that, again, this is at least in part a burp from eating its companion. Time for more scotch. Those of you at Liberty missed my opening about the scotch. I had a friend give me a glass of a very, very nice scotch, single malt scotch, and it's really, really a nice scotch. And I didn't get it finished before it was time for the panel, so doggone it, I brought it with me. All right, next slide. All right. Now, we've known since at least 1836 that Betelgeuse was a semi-regular variable star. What does that mean? Well, it means the variations don't always follow the exact same pattern each time. There may be cycles of differing lengths. The variability may become very irregular, or it may actually cease for a period of time. And Sir John Herschel was the discoverer of the variability. This variability comes in the form of radial pulsations, which means that in this regard, Betelgeuse is an intrinsic variable. However, there is a secondary long period variation whose cause is not known. And this may be because of hot spots. Remember I said Betelgeuse was boiling. Okay, it's extremely hot. There are convection currents within it. And so there may be some truly gigantic convection cells. And so these are the hot spots where convection cells meet up. Kind of like a hot spot in the Earth's mantle produces a volcano, that kind of concept. But these convection cells would occupy a rather large chunk of the stellar radius, and couple that with the star's axial rotation, and you can get some bright hot spots that come into and out of view as the star rotates. If any of these were the case, that would make Betelgeuse a hybrid intrinsic extrinsic variable. The amplitude of that variation is about one magnitude, one astronomical magnitude, which means it varies by about a factor of 10 over the course of its oscillations. Next slide. And so this gives you an idea. These are called light curves. For those of us that study variable stars, this is what you want to look for. This tells you a lot about the star. And so these are examples of what a light curve for Betelgeuse looks like. Now you'll note that it's kind of irregular there, which is a factor, which is a key constituent, a key identifier of Betelgeuse's variability. Next slide. Now, let's talk a little bit about stellar evolution. This is a very, very important chart called the Hertzsprung-Russell Diagram. It's named after the two astronomers who developed it. The horizontal axis, you can think of, it's got a couple of different labels there, but you can think of that as the temperature of the star. The vertical axis is the brightness of the star, again, shown in a couple of different scales. But that's basically what it is. And you'll notice that there are several curves on this chart. And what we have found is that these curves are populated by stars at different points in their lives. The main sequence, which is roughly the diagonal, sort of the slightly wavy diagonal, is where a star will tend to spend the bulk of its life. When it is first forming, I can't remember if I hit the next slide. Yeah. This gives you an idea of where any given type of star can be found. You'll also notice that there are variable stars, categories of variable stars to be found in specific parts of this diagram. Next slide. I may want you to back. Okay. This outlines specific stars and where they are to be found. If you read Travis Taylor's books, you'll see Tau Ceti, Alpha Centauri A, Sirius, Vega, Rigel, and all the way up there at the top, there's Betelgeuse. Next slide. Now, this gives you a quick outline of stellar evolution. Over on the far left, we have a molecular cloud, such as we find a truly gigantic one over in Orion. It gradually begins to collapse under gravity until it forms what's called an open cluster of protostars. Some of those simply aren't big enough to initiate fusion in the core. Those become brown dwarfs. Actually, there's a very strong argument that Jupiter is a brown dwarf. They do tend to output energy, but they don't output necessarily light. Radiation and some infrared to radio wavelengths, but no visible light. A low-mass star like the Sun will eventually form something like what we see in the middle. And then an extremely massive star forms what's called an O or B type star, which is a blue-white supergiant. As the star burns hydrogen in the core, it begins to exhaust its fuel supply over time. How big the star is determines how fast it does so, but not in the way you might think. You might think that a really, really big star would last a long, long time. It doesn't. It's the shortest lived of the stars. A really, really big star has so much pressure at the core that it is fusing hydrogen into helium at incredible rates. The smaller the star is, the less pressure it has in the core, and the longer it lasts because the fusion rate is lower. So eventually, what happens though is that the core begins to exhaust its hydrogen. Once it's exhausted its hydrogen, fusion slows down and then eventually stops. But the star's not dead yet. I'm not dead yet. I'm getting better. What happens next is that gravity begins to overbalance the pressure from the energy output. And the core of the star begins to collapse. But as it collapses, the actual physical pressure of the gases goes up. Eventually that pressure gets high enough that, boom, helium starts to burn. And we call that helium flash. Now, when helium burns, when helium fuses, it releases more energy in fusion than hydrogen does. So now we have a higher temperature in the core. We have more radiation moving outward from the core. The star as a whole expands. Now we move into, depending on the size of the star, a red giant or a red supergiant. Is everybody following me so far? All right. Now, in the case of a relatively small star, helium fusion might be as far as it gets. It may simply not be big enough to fuse heavier elements. And if that's the case, then the next time it runs out of helium and starts to collapse, it doesn't have enough oomph to start fusing any of the heavier elements, lithium or carbon, etc. And so the core of the star collapses, and the outer layers of the star kind of go poof. Okay, ladies, I know you've had experiences with loose powder and powder puffs. What happens when you drop the powder puff into the loose powder? Poof. Okay. Well, that's what a planetary nebula is. It's a poof. It's a big bubble that consists of the outer layers of the star. All right. In the center, if you look very, very closely at that image there, you will see that there's a tiny, tiny, tiny little dot. That's what's left of the core of the star. It is a white dwarf, and eventually, as the white dwarf cools off, it will become a black dwarf. And that is a stellar tombstone. Star's dead. Nothing more going to happen to it. Now, if it's a little bit bigger, or if it happens to be in a binary system, you can get some mass transfer to the other companion. And you can either get a nova explosion and then drop to a white dwarf, or you can get a type 1a supernova, which is a big bada boom. Basically, what you have there is you've got a star that's a little bit bigger, and it's managed to achieve fusion of heavier elements. However, the heaviest element that it can form is iron. Any element heavier than iron actually takes more energy to fuse than is put out in the fusion reaction. Why? Because it so happens that the nucleus of iron is almost exactly 1 angstrom. And 1 angstrom happens to be the radius of operation of something called the nuclear force. The nuclear force is that force which actually holds the subatomic particles together in the nucleus. So if you've got a proton over here and you've got a neutron over here on the opposite side of the nucleus, iron has a radius of 1 angstrom, diameter of 1 angstrom, so this guy can just manage to reach over and tag this guy. However, if you go with something heavier, like, say, uranium, this guy over here is trying to reach all the way over here. Can't do it. So it's not as, the nucleus of a heavier element is not as tightly held together, which is why they tend to fall apart, and we call it radioactivity. All right? So far, so good. So the star has just formed iron in its core. It's finally reached the point where it's fusing elements into iron. There's a number of different ways it can reach that point. I'm not going to go into that kind of detail. Once it does that, the star is on its deathbed. Once it's exhausted all of its core fuel in making iron, there's nothing else to do. So the star begins to collapse, but because it's massive enough, and here we're actually starting to get up into the top range here, because it's massive enough to do that, suddenly you wind up with a gravitational collapse that is starting to move at relativistic speeds. The collapsing material is falling inward towards the center at speeds at or exceeding 0.1 C. Now, the core kind of goes, and suddenly the pressure is such that the electrons are forced into the nucleus, where they bind with the protons to become neutrons. And all at once, the core of this star has become one gigantic ball of nothing but neutrons. This is called nucleon degenerate matter, and it is the strongest stuff that we know. It's also called a neutron star. However, the outer layers of star are still falling inward at relativistic velocities, and they don't know that yet. And what happens next is literally the irresistible force meets the immovable object. The outer layers of the star impact the surface of the neutron star and rebound. And suddenly you have energy and to spare, and that's how you make heavier elements. So, it's also how you make a type 2 supernova. And then if it's really, really big, not even nucleon degenerate matter is strong enough to withstand the gravitational collapse. In which case the whole thing goes right down the hole, the black hole. So far, so good? Any questions? All right. Next slide. Now, this is a step-by-step of where on the Hertzsprung-Russell diagram, or HR diagram we call it for short, because let's face it, Hertzsprung-Russell is a mouthful. This is a little diagram of where the star is moving through this diagram as it evolves. So you see up in the top left, that version of the diagram, you have a Bach globule. That's what you typically see is the little, if you look at a lot of Hubble photos, you see the tiny little globs that almost look like droplets or something. Those are called Bach globules. Those are stars trying to form. This is where the gas and dust in the area has begun to condense. It's begun to collapse under its own gravitation, but rotation forms it into a sphere. And then eventually it continues to contract. It becomes a protostar. Fusion ignites in the center, and it slowly drops onto the main sequence. Where on the main sequence is determined by how large it is, which in turn determines how hot it's going to be. It stays on the main sequence for a long, long time. This is the bulk. This is easily 90 to 95% of the stellar lifetime is spent on the main sequence. As, however, it begins to exhaust its fuel and it expands and becomes a red giant, it moves off the main sequence and up to the top right corner, as we see on the top right graph. And we have helium flash, and it'll, depending on how big it is and how many flashes, how many elements it goes through fusing, it'll oscillate back and forth up there for quite a while. Not nearly as long as it's spent on the main sequence, but it'll go back and forth. Then eventually, when it runs out of oomph, and the majority of stars are not very big. The majority of stars are like the sun. They're going to wind up as a white dwarf. So then it eventually goes poof, and you have a planetary nebula, and the core shoots over to the left. It is now hot. Well, it is much less hot than it was. It's also quite still bright. And so it moves from the top right to the top left, and then as it cools and dims, it drops down into the white dwarf area, and then eventually into a black dwarf and kind of falls off the bottom. Next slide. So that's the whole thing put together. And so you can follow it from Bach globule about the middle on the right, then follow the green line until it settles onto the main sequence, runs out of fuel, helium flash, now it's a red giant, runs out of anything it's got left, and down to the white dwarf area. Next slide. Now, for those of you that are worried about the sun, this is the sun's forecast evolution in detail. We're still sitting on the main sequence. We're maybe halfway through the sun's lifetime. We got nothing to worry about anytime in the foreseeable future. It's entirely possible that by the time our sun balloons up into a red giant, we won't even be around. Now, you can interpret that however you want to, as being the species is gone or the species has moved somewhere else. Personally, I'd like to think we move somewhere else. But then eventually it's going to wind up down there with Procyon B and Sirius B. Eventually. Next slide. Notice, however, that is a little bit different the bigger the star. Also notice that it kind of really doesn't drop down into the white dwarf area for the really big stars, because they don't do that. They go kaboom. And frankly, I couldn't find a chart, and I didn't really sit down. I'm not, my husband is the graphics artist. I can't draw a straight line with a ruler, literally. Either the ruler slips or I get my thumb in the way. So I didn't even try to draw one of these because you wouldn't like the result. But actually, if you go about another 5 solar masses up the chart, maybe 10, that's where you're looking at placing Betelgeuse. All right, next slide. So that gives you a little bit better idea there. The blue to purple is more like where Betelgeuse would be. And that's why I stuck that in there, because that gives you a little bit more idea. But again, it doesn't really drop down. It just kind of goes over there and blows up. Next slide. So Betelgeuse has evolved off the main sequence and into a red supergiant, and that was likely aided by munching its companion. Think of it as being like a black widow spider, I guess, or a praying mantis. And it was likely already on the way when it cannibalized its companion, but still that left it as a really, really honking big star. It was probably a big star to begin with, but because more massive stars live shorter lives, it was probably no more than about 10 to 12 million years. Contrast that with the sun, which we're already talking, the Earth is about 4.5 billion years old. And the sun's older than that. So, 10 million versus, say, 5 billion. Big difference. So it was probably about 8 million years old when it began to evolve off the main sequence. It's probably been off the main sequence for about 1 million years. It's probably been a red supergiant for about 500,000 years. And it absorbed its companion about 100,000 years ago. So we don't really know how long it's got left. It may have another few million years, or it could go bluey tomorrow. The consensus appears to be sometime in the next 100,000 years, which could get interesting for us. Next slide. Now, we needed all that information that I just went over in order to understand what's happened in the last couple of years. In late 2019, Betelgeuse began dimming deeper than it's been seen to do in recent years. It has been seen to go that deep, but not any time recently, and it always bounced back pretty quickly. So remember what I said, that if it runs out of fuel in the core, fusion ceases, and it's going to start collapse. Well, many people thought that this might be a sign that the fusion had indeed ceased and that the core was collapsing. Why? Because if the fusion in the core has stopped, then the energy is not reaching the outer layers of the star to be radiated to us. So far, so good? Next slide. This gives you an idea of what I'm talking about here. On the left is Betelgeuse at an average, normal kind of brightness. And then on the right, the red star is Betelgeuse about late 2019 and early 2020. So you can see the difference in brightness of the two time frames. It's the same star, 2 time frames. Next slide. Again, Betelgeuse at max and min. January 22nd, 2020 versus January 4th, 1986. So it's comparable time of the year, but very, very different in brightness. Next slide. Well, what would happen if it's supernovaed? Are we in for it? No. It turns out that you would need the star to be within, a supernova to be within about 100 to 150 light years of Earth for Earth to be in trouble. If you'll remember back when I gave you the original stats, we're looking at a minimum of 600 light years away for Betelgeuse. So, no, there's no risk to us. However, that doesn't mean we wouldn't see it. And we do think that one of the major mass extinctions in geologic history may have been caused by an extremely close supernova. Next slide. Now, what would it do? Well, like I said, we don't have any imminent threat, but it would definitely change the night sky. We believe that a Betelgeuse supernova would be at least as bright as the half moon. It would also be visible during the daytime. So you're looking at, and of course it's going to dim over time, but it's probably going to take 3 to 6 months for it to dim to the point where it's no longer visible in the daytime. The supernova would be so bright that it would cast shadows at night. It might affect lunar navigation by animals that do such things. It might even disrupt astronomical observations because of the brightness. We already have to watch. There are many observations that astronomers cannot make during certain phases of the moon. Now, if you got Betelgeuse up there and it's as bright as, at least as bright as a half moon, now you got another problem to worry with. Next slide. Now, the biggest current threat is probably a solar proton event. And these would not be a good thing. Unfortunately, if Betelgeuse does supernova, it may trigger a solar proton event. And so that is a source of concern for the simple reason that it would affect our tech. It would affect navigation. It would, anything that's not hardened against, say, an EMP, it has the potential for causing problems, to causing damage to the electronics. So yeah, it's a concern. It's not an extinction event, but for a technological civilization, it might not necessarily be a great thing. Next slide. However, late last year, Betelgeuse began to brighten again, very noticeably so. Next slide. And so you can see right at the tail end of this curve, you can see the upturn. And so it dropped. Oop, that's going back up. Next slide. And you can see the difference here. However, notice that what looks like a circle on the left does not look like a circle on the right. The bottom half of the star has dimmed a considerable amount. The top part of the star is actually brighter than normal. And notice it's also estimated to be about 400 times larger than the sun. Next slide. So the trick here is figuring out what caused it. And remember that we knew that there were hot spots in the photosphere that caused some irregularity in the variability. Remember also that it pulses. Remember also that it is thought that it may have thrown off a burp, if you will, from consuming its companion. And remember that it rotates extremely rapidly. The current thought, I won't say it's a consensus because we all know about consensuses in science. That's supposed to engender a laugh, but maybe it's a little bit too much of a groan. But we believe that what may be happening is that there may be material that has been thrown off of the star by both the cannibalization of its companion and by its rapid rotation, and that this material is getting in the way. It's going to be clumpy. It's going to be in orbit around the star. So you're going to get big blobs moving into and out of our field of view. And if you combine that with the fact that it pulses, but that it pulses somewhat irregularly, what we may have had happen is a combination of a deep pulsation with an exceptionally large, dense blob of gas and dust that simply orbited around until it got in our way. And if we postulate a big enough clump of gas and dust, we may not even have had to worry that much about where it was in its pulsation rate. Next slide. So, in other words, it ain't supernovaed yet. And that's disappointing because, let's face it, that would be really, really kind of cool. Not necessarily good for our tech, but really cool. I mean, think about it. A star visible in the daytime. Plus, if it's close enough for us to see the disk of the star, that means we're probably also going to have a really, really cool looking nebula when the whole thing is said and done. However, it wasn't that. It was just Betelgeuse being Betelgeuse, as usual. So, yes, I did do quite a lot. Just keep scrolling through until it ends. I did do quite a lot of research for this. Some of this was just me talking off the top of my head based on my knowledge. And some of it was trying to dig up good-looking photos to illustrate what I wanted to say. And some of it was finding out exactly what the heck was really going on with it. So, but anyway, Rich asked me to put something together about this, and so I did. So, any questions? Yes. Yes and no. Actually, the magnetosphere already does a pretty good job. And since protons are charged particles, they're probably going to tend to get caught up in the magnetosphere. It's probably going to cause some problems just because they already have to worry about that. Most people don't realize that photographic film is sent up to the ISS in metal canisters. After 2 weeks, you're starting to see a noticeable fog of the film, unused film. After 3 months, it has to be thrown out because of the radiation penetrating the metal canisters. So there's already a certain amount of that happens. So yes, you're going to add to it, but because, like I said, because it's a charged particle, you're going to get more in the magnetosphere. We might have some really nice auroras. It's not going to be really great for polar regions. But yeah. Next question. Yeah. Well, with something like Betelgeuse, where you're actually able to see the stellar disk, you can actually use a Doppler, use a spectroscopy and get the Doppler shift from one side to the other. So you can actually determine the rotation rate there. As far as the boiling is concerned, I think part of that is, again, some of the spectroscopy. You can do an amazing amount by grabbing the spectrum of a star. You can pull out so much information, it's unreal. So you can get, you can determine what elements are in the atmosphere. You can determine where in the atmosphere. You can determine rotation rates. You can just all kinds of stuff like that. So there's various and sundry spectroscopic techniques that you can pull stuff out with. You can also look at different spectral regions, and they will show you different details of the star. So it's none of it is really that advanced observation. Describing how it's done to a layperson, I'm not the best at that, but it's not a difficult observation. It's not a difficult analysis. Yes. Oh, it's going to eventually. Okay. The question is, how if it supernovas, how long will it take for it to affect us? Well, let's put it like this. If it supernovaed today, right this instant, we wouldn't know about it for at least 600 years. However, if it supernovaed 600 years ago, we'll be knowing about it tomorrow. So it depends on how far away it is. The fastest any of this information can travel is the speed of light. So it isn't going to go faster than the speed of light. Probably would take a little bit longer for the protons to get here, but the protons are more than likely going. Well, the protons come from the sun, but excuse me, the radiation from the supernova explosion is going to reach the sun from Betelgeuse in about 600 years. And then a few hours past that, we go, whoa, here come the solar protons. Next question. Come up here and talk into the mic so I don't have to repeat that. I want to make sure that the people at Liberty can hear.
Yeah, but I have a face for radio and a voice for newsprint. There's a star that I was just reading about the other day, VVV-WIT-8, that disappeared for about 200 days, and it caused a little bit of excitement.
Yeah, that particular star is believed to constitute what they're looking at possibly being a new class of extrinsic variable. And what is happening there, we believe, is that there is a circumstellar disk, and that it may not be a uniform disk, but basically it's a kind of eclipsing variable where the clouds in the circumstellar disk are what diminish the star. It's probably also in a binary system. So if you wind up with I want to use my hands for this, so bear with me here. All right, so if you wind up in a binary system, yes, please. So you wind up in a binary system, and if one of those stars in the system has a very, very large circumstellar disk, as one passes in front of the other, as the one with the disk passes in front of the other, you actually wind up with the eclipse starting out here. And so disk, 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 star, 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 disk, 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 disk. Oh, now it's gone. Okay? Does that make sense what I'm saying? All right. So that is what they think is happening with that particular star. And that they're thinking about classifying that as an extremely long period eclipsing variable, with the caveat that part of what is doing the eclipsing is a circumstellar disk about one of the stars. Now, what do circumstellar disks tend to form? So I'm actually going to start looking into that star to see where it is in its stellar evolution, because if it's young enough, we may be looking at a baby stellar system. We already know that planets form in binary and even trinary systems, because the nearest star to us is wrong. It's Proxima Centauri. Smart. So the Alpha Centauri system is a trinary system. It consists of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. The center of mass of the system is 4.3 light years away. Proxima currently is 4.2 light years away. Interestingly, Alpha A, Alpha B, and Proxima are all known to have planets. So I'm very interested in digging deeper into that particular stellar system to see what we've got. Any other questions? Yes. Correct. Yes, but no. If you couldn't hear, he said if Betelgeuse was really collapsing, he understood that the collapse would occur really, really fast. What happens is the collapse accelerates. But what starts it off is it starts running out of fuel. And so as it runs out of fuel, it's not completely out of fuel yet. So it's still fusing heavier elements, but at a lower and lower rate. And as that rate diminishes, the energy output from the core diminishes. As the energy output from the core diminishes, the brightness of the star diminishes. Once fusion ceases, the collapse becomes very, very rapid. Does that make sense what I'm saying? Okay. No, you're right. Once fusion ceases, the collapse becomes very fast, and it becomes, like I said, relativistic. So you're looking at 0.1 C or better. No, you can't fuse iron. It takes more energy to fuse iron than you get in the fusion process. But once it reaches, once a substantial amount of iron has been produced in the core, that's when the diminishing returns begin. That's when the star starts dimming. Because there's just not enough there to fuse to keep the original brightness. Yes? They'll fuse higher than iron, because now you've got potential energy and kinetic energy to waste. So yeah, it doesn't matter that it takes more energy to produce the element than you get in the course of the element of fusing the element. You just that's where uranium and plutonium and all that stuff, that's where it all comes from. All right, guys, it's about that time, and I got somebody waiting on me, so that's it. Hope you enjoyed it.